All right, so today we are in topic 10, representing and interpreting data. We are on page 323 all the way to 330 today. And our goals and objectives for today are to use data from a random sample to make inferences about a population, find measures of center and measures of variability, including interquartile range and mean absolute deviation. So before we get started today, what we're going to do is we are going to watch a quick video from khanacademy.org. If you haven't used khanacademy.org before, it is a great resource so that you can learn multiple sets of very important prerequisites so that you're able to do all types of math that we're learning now, like mean absolute deviation, finding the mean, uh, max, minimum, the upper quartile, the lower quartile. So, what you need to have in your bag of skills right now is adding, subtracting, multiplying, and dividing. If you don't have that yet, you definitely want to work on that, because this is something that if you don't have those skills, you are definitely going to need to use a calculator, but it can still be done. So we're going to start off by watching this video, and then we will be going into our topic 10 block 4 assignment and actually putting some of this that we learned from this video into our everyday class. So without further ado,
I've got two different data sets. So the first data set, I have 2, another 2, a 4, and a 4. And then in the other data set, I have a 1. I'm going to do this on the right side of the screen. A 1, a 1, a 6, and a 4. Now, the first thing I want to think about is, well, is there a number that can give me a measure of a measure of center of each of these data sets? And one of the ways that we know how to do that is by finding the mean. So let's figure out the mean of each of these data sets. So this first data set, the mean, well, we just need to sum up all of the numbers. So it's going to be 2 plus 2 plus 4 plus 4. And then we're going to divide by the number of numbers that we have. So we have 1, 2, 3, 4 numbers. So that's that 4 right over there. And this is going to be 2 plus 2 is 4, plus 4 is 8, plus 4 is 12. So it's going to be 12 over 4, which is equal to 3. So actually, let's see if we can visualize this a little bit on a number line. So and actually I'll do a little bit of a dot plot here so we can see all of the values. So if this is 0, 1, 2, 3, 4, and 5. And so we have 2 2's. And so why don't I just do, so for each of these 2's, actually, I'll just do it in yellow. So I have 1, 2, and then I'll have another 2. I'm just going to do a dot plot here. And then I have 2 4's. So 1, 4, and another 4 right over there. And we calculated that the mean is 3. The mean is 3. A measure of central tendency, it is 3. So I'll just put 3 right over here. I'll just mark it with that dotted line. That's where the mean is. All right, well, we've visualized that a little bit, and that does look like it's the center. It's a pretty, it makes sense. So now let's look at this other data set right over here. So the mean over here is going to be equal to 1 plus 1 plus 6 plus 4. All of that over, we still have 4 data points. And this is 2 plus 6 is 8 plus 4 is 12. 12 divided by 4, this is also 3. So this also has the same mean. We have different numbers, but we have the same mean. But there's something about this data set that feels a little bit different about this. And let's visualize it to see if we can see a difference. Let's see if we can visualize it. So now I have to go all the way up to 6. So let's say this is 0, 1, 2, 3, 4, 5, 6. I'm going to go one more, 7. So we have a 1, we have a 1, we have another 1, we have a 6, and then we have a 4. And we calculated that the mean is 3. So we calculated that the mean is 3. So the mean is 3. So when we measure it by the mean, the central point or measure of that central point, which we use as the mean, well, it looks the same, but the data sets look different. And how do they look different? Well, we've talked about notions of variability or variation, and it looks like this data set is more spread out. It looks like the data points are more, on average, further away from the mean than these data points are. And so that's an interesting question that we ask ourselves in statistics. We just don't want a measure of center, like the mean. We might also want a measure of variability. And one of the more straightforward ways to think about variability is, well, on average, how far are each of the data points from the mean? And that might sound a little complicated, but we're gonna figure out what that means in a second, and not to overuse the word mean. So we want to figure out on average how far are each of these data points from the mean. And what we're about to calculate, this is called mean absolute deviation. Absolute deviation. Mean absolute deviation, or if you just use the acronym MAD, MAD, for mean absolute deviation. And all we're talking about, we're going to figure out how much do each of these points, their distance, so absolute deviation, how much do they deviate from the mean, but the absolute of it, so each of these points at 2, they are 1 away from the mean. Doesn't matter if they're less or more, they're 1 away from the mean. And then we find the mean of all of the deviations. So what does that mean? I'm using the word mean, well, using it a little bit too much. So let's figure out the mean absolute deviation of this first data set. So we've been able to figure out what the mean is. The mean is 3. So we take each of the data points and we figure out what's its absolute deviation from the mean. So we take the first 2. So we say 2 minus the mean. 2 minus the mean, and we take the absolute value. So that's its absolute deviation. Then we have another 2. So we find that's absolute deviation from 3. Remember, if we're just taking 2 minus 3 and taking the absolute value, that's just saying it's absolute deviation. How far is it from 3? It's really easy to calculate in this case. Then we have a 4 and another 4. So let me write that. So then we have the mean, or we have the absolute deviation of 4 from 3, from the mean. And then plus, we have another 4. We have this other 4 right up here. 4 minus 3. We take the absolute value because once again it's absolute deviation, and then we divide it, by the number of data points we have. So what is this going to be? 2 minus 3 is negative 1, but we take the absolute value, it's just going to be 1. 2 minus 3 is negative 1, we take the absolute value, and it's just going to be 1. And you see that here visually. This point is just 1 away. It's just 1 away from 3. This point is just 1 away from 3. 4 minus 3 is 1. Absolute value of that is 1. This point is just 1 away from 3. 4 minus 3, absolute value, that's another 1. So you see in this case, every data point was exactly 1 away from the mean. And we took the absolute value so that we don't have negative ones here. We just care how far it is in absolute terms. So you have 4 data points. Each of their absolute deviations is 4 away. So the mean of the absolute deviations are 1 plus 1 plus 1 plus 1, which is 4 over 4. So it's equal to 1. So one way to think about it is saying, on average, the mean of the distances of these points away from the actual mean is 1. And that makes sense because all of these are exactly 1 away from the mean. Now let's see what results we get for this data set right over here. And I'll do it. Let me actually get some space over here. At any point, if you get inspired, I encourage you to calculate the mean absolute deviation on your own. So let's calculate it. So the mean absolute deviation here, I'll write MAD, is going to be equal to, well, let's figure out the absolute deviation of each of these points from the mean. So it's the absolute value of 1 minus 3, that's this first one, plus the absolute deviation, so 1 minus 3, that's the second one, and then plus the absolute value of 6 minus 3, that's the 6, and then we have the 4, plus the absolute value of 4 minus 3, and then we have 4 points. So 1 minus 3 is negative 2. Absolute value is 2. And we see that here. This is 2 away from 3. We just care about absolute deviation. We don't care if it's to the left or to the right. Then we have another 1 minus 3 is negative 2 with absolute value. So this is 2. And that's this. This is 2 away from the mean. Then we have 6 minus 3. Absolute value of that's just going to be 3. And that's this right over here. We see this 6 is 3 to the right of the mean. We don't care whether it's to the right or the left. And then 4 minus 3. 4 minus 3 is 1. Absolute value is 1. And we see that. It is 1 to the right of 3. And so what do we have? We have 2 plus 2 is 4, plus 3 is 7, plus 1 is 8 over 4, which is equal to 2. So the mean absolute deviation, let me write it down, it fell off over here. Here for this data set, the mean absolute deviation is equal to 2, while for this data set, the mean absolute deviation is equal to 1. And that makes sense. They have the exact same means. They both have a mean of 3, but this one is more spread out. The one on the right is more spread out because on average, each of these points are 2 away from 3, while on average, each of these points are 1 away from 3. The means of the absolute deviations on this one is 1. The means of the absolute deviations on this one is 2. So the green one is more spread out from the mean.
All right, so with what we just learned, what we're going to do is I want you to think about the mean. The mean in this case that we're looking at right here in this specific student council survey, that right there is known as a balance point. And the reason that it's known as a balance point is because everything to the left of it weighs exactly the same as everything to the right of it. Or if you were to add it all up, everything to the left would be equal to everything on the right. So the mean is balancing our data, okay? So are there ways to measure variability other than using like mean absolute deviation? What's another way that we use variability?
Box plot.
Well, in the box plot, what do we use to see how far the maximum is from the minimum?
The range.
The range.
Or the whiskers.
So we can use the range to measure variability. All right. So with that being said, if you would, Devin, would you go ahead and read all of this for us, please, sir?
Yes, sir. You can always quantify the variability of the data in terms of the mean. This measurement is called the mean absolute deviation. It measures the average distance each data point is from the mean. Play the animation to find this measurement. For this exploration, use a smaller data set so you can easily calculate the measure. This is one of the smaller sets of students' responses the student council gathered. How far away from the mean of 5 are the values in the data set? The sum of the distances from the mean to each value on the left of the mean should equal the sum of the distances from the mean to each value on the right of the mean.
Perfect. All right. So with that being said, what we're going to do is we're going to see if they differ any. So what we're going to do is we're going to see if we were to do 5 minus 4, we would get 1. 5 minus 2, we would get 3. 5 minus 0, we would get 5. And 5 minus 0, we would get
5.
So the total of that sum would be
14.
Correct. So we do the same thing to the other side, but it's a little bit different. Since it's bigger, what I like to do is subtract. So what I do is I do 7 minus 5 is 2, 8 minus 5 is 3, 9 minus 5 is
4,
and 10 minus 5 is
10.
And
5.
All right. And when we get the sum of those, it is also what?
14.
It is also 14. So that is why the mean is our balance point. If it was moved to the left or the right a little bit, it wouldn't be balanced anymore. It would be weighted on one side, and that would make our number line tilt. So, with that being said, what we're going to do is we're going to see what would happen if we didn't use the absolute value of the differences. How would that sum change? So on the left side of the mean, I said to do 5 minus 4, 5 minus 3, 5 minus 2, and 5 minus 0. Well, if we did that on the right side and I said 5 minus 7, that would be what?
-2.
It would be a negative. So you would get a negative for all of those results, which would result in a negative what?
Negative answer.
Correct. And it would be negative 14. And we know that 14 plus
Yeah.
negative 14 is what?
0.
0.
Zero.
That wouldn't be balanced, would it?
No.
No. So we need to make sure that we're using the absolute value when trying to figure out the mean absolute deviation, because what we're trying to do is we're looking at the distance that the data is away from the mean. And that's actually what the mean absolute deviation is. It measures the average distance each data point is from the mean. So we're going to look at page 2 or slide 2 of page 10. And you'll notice that now we're taking the sum of the distances from the mean. And if we get the sum of 14 and 14, what's that going to be? That would be 28.
28.
Good. And so, Vincent, once we get 28, you'll notice that we're dividing it by 10. Why do you think we're dividing it by 10, Vincent?
Because we have 10 samples.
Good job. We do. We have exactly 10 samples. So what we do is we take 28 and we divide it by 10 because there are 10 dots here. And whenever we do that, Tamarian, what is our mean absolute deviation?
2.8.
Great job. So notice that less than 50% of the values lie within one mean absolute deviation of the mean. So this indicates that the data is spread out. So what I mean by that is if you look at the mean absolute deviation and you draw it out from your mean on both sides, there's only one point on each side within that mean absolute deviation. So since this is the case, that means that our data is spread out. If it was more inside of there, then that would mean that our data is what?
Compact.
Yeah, or close, correct. All right, so if you would you read this for us, please, Miss Alora?
Can you repeat that?
Could you read this page for us, please, ma'am?
Yes, sir, I can.
Thank you.
A large mean absolute deviation indicates a lot of variability in the data. Student council survey results in multi-purpose track usage. What is the mean absolute deviation for the entire set of data gathered by the student council? What does the mean absolute deviation indicate about the variability of the data?
All right, so what we're going to do is we're going to take what we just learned and we're going to apply it to this. So if you don't have good memory, the mean from yesterday, does anybody know?
It was 3.64.
It was 3.64. The mean was 3.64. And we know that to determine the variability, we need to take that mean of 3.64 and do what with each set of points? Get the
We need
started with an
we
A.
need how I don't know what that word
Absolute.
to describe it is. Yeah, absolute.
We got to get the absolute value of each one of these, how far it is from 3.64. So the easiest thing to do is to subtract each time. So what is 3.64 minus 3?
0.64.
Perfect.
Yeah.
And how many dots do we have?
4. So,
So-
we multiply that times 4.
Correct. We would do 4 times this. All right. Now let's do the next one. What is 3.64 minus 2?
1.64.
Correct. And what would we multiply it by?
9.
9. All right. What is 3.64 minus 1?
2.64.
Perfect. What would we multiply it by?
3.
What would 3 minus 0 be? 3.64 minus 0 be?
3.64.
And what would we multiply it by?
10.
Good. Now we get to the more complicated side. I'm just going, since we're using absolute value, if I do 3.64 minus 4, I'm going to get a negative number. So in order not to do that, what I'm going to do is I'm just going to subtract with 4 and then subtract 3.64 from it. So what's 4 minus 3.64?
1.64.
Try again. 4 minus 3.64.
You take 3.64 away from 3. 0.64?
Check it. We got 10, 9, 3. 10 minus 4 is?
0.64.
And 9 minus 6 is?
3.
So we get what?
0.36.
Good. And what do we need to multiply that by?
8.
All right. 5 minus 3.64.
1.36.
Good. Y'all are starting to catch on to it now. What would I multiply it by?
3.
3.
Good. What would 6 minus 3.64 be?
2.36.
Yep. How are we? What is there a pattern here or something? I feel like y'all aren't working hard to do this.
It goes up by 1.
There we go. So since it's going up by 1, what does 7 have to be?
3.36.
And what would it need to be multiplied by?
2.
Oh.
What about the next one?
4.36.
4.36.
What's it going to be multiplied by?
2.
3.
3?
Yeah, 3. I'm looking
There
at
we
the
go.
next one.
All right, so we're doing 2 times something on that next one. 2 times what, Angel?
I don't know.
5.36.
Good. Akira, what am I going to do on the next one, on that 10? Man, I feel like this is really easy. I don't think y'all are paying attention. Who can help her out? Braden, can you help her out? Or Brendan, or Satari, or Erica, or Aubrey, or Alora, Khalees, Rachel, Sophia, Timarian, Vincent. It's one more than 5.36, which would be... What's one more than 5?
6.36.
Good. Good. What would this one for 12 be?
8.36.
Why is it not 7?
Because we skip 11.
Correct. All right. Now, what do I have to do with every bit of this information?
We have to add it all together.
Once we add it together, what do we do next?
Divide by 50.
Why is it divided by 50?
Because there's 58 total samples.
Correct. So when we add all this together, we're going to get 128 point. No, I was wrong. 123.28. I was really close.
Thank you for saving us time.
Yes. So we're going to take 123.28, or 123 and 28 hundredths. We're going to divide it by 50, and this will be our mean absolute deviation. So we're going to get somebody other than Devin and Angel to help us for a second, because they've been killing it. Rachel, how do I put this in the calculator to get my answer?
the 1.28.
All this. How do I put all that in the calculator?
So you're gonna do 103.28 divided by 50.
Good. When we do that, what is our mean absolute deviation going to be?
2.46.
Okay. So 2 and 4,656 ten thousandths. All right. That is our mean absolute deviation. And you are 100% correct. So if we come down here, we'll see that. And you'll notice that over half of the data is what, Vincent? My boy Vincent ain't been answering real fast today. Over half of the data lies within one mean absolute deviation of the mean from 1 and 1800ths to 6 and 1/10. This indicates that there is not too much variability in the data. So, what we're going to do is we're going to take what we know here. We're going to answer a question on the next page. So we should have questions 1 and question 2 answered already on page 323 in our workbook. And now we're going to answer question 3 on page 12 of our Agile Mind sampling and variability. Miss Angel, go ahead and read this for us, please, ma'am.
As you have been seen representing a set of data in different ways can help you understand the data more completely. Now can you solve the puzzle to demonstrate your understanding?
All right. So looking at this, Angel, look at this first one. It says the majority of the students responded that they would use the track less than 6 hours per week. Is that true or false? Angel's not paying attention to me. Angel. Angel. The majority of the students responded that they would use the track less than 6 hours per week. Is this true or false? Help her out, class. I think she's lost. Sophia, help her out.
I'm lost too.
Oh, goodness. So let's pay attention. It says 6 hours per week or less. So that's starting from right here and saying this way. So that's saying that most of the data is 6 hours or less. Or is most of the data over here?
It's true.
It would be true because most of the data,
Majority of the students want to use the track field or the multipurpose track field less than 6 hours or 6 hours a week.
correct. All right. Khalees. It says that 5 students responded 8.5 hours per week. Do you see that anywhere in that data, Khalees? That 5 students responded that they wanted to be out there for 8.5 hours per week?
No.
I don't either, so I think that's false. The interquartile range, remember we had to find that yesterday. Satari, to find that interquartile range, we had to take the upper quartile and the lower quartile, and we did something with them. So this says that the interquartile range is 6 hours. Is that true or false, Satari?
True.
All right. So we're going to take our upper quartile and our lower quartile. And remember, to find our interquartile range, we take this and we subtract our lower quartile from it. So we have 6 minus 1. So what is our interquartile range going to be, Satari?
5.
5. So this says the interquartile range is 6. Is that true or false?
False.
It is false. And finally, it says the most frequent response was 0 hours per week. What do you think, Erica? Is that true or false? If you're looking at the dot plot right here, Erica, which response was picked the most? What number has the most dots on it? What do you think, Erica? Help her out, Brendan. Help them out, Braden. There's Brendan.
I think it's true.
It is true because 0 showed up the most. Good job. Perfect. So the dot plot tells you that more students answered 0 hours than any other, and the box plot shows that the interquartile range and shows where most of the responses are lying. All right, so with that being said, this actually concludes our lesson that we're going to do in our workbook on Webster Agile Mind today. But I do have a closing question for our part of the book that we're working in, and that would be, when might the interquartile range be a better measure of variability than the MAD? When might the interquartile range be a better measure of variability than the mean absolute deviation? Waiting on y'all. What do you think? When might the interquartile range be a better measure of variability than the mean absolute deviation?
When the interquartile range is less than
Okay.
the MAD.
Okay. Along with that, I would also say if you needed your data quickly, it's a lot easier to look and find your interquartile range in a box plot than it is to take a dot plot, take the information, find the mean, then find the mean absolute deviation. So it's a lot quicker just to find the interquartile range, right?
Yes, sir.
If it's simple data. So I would say when we're looking at simple data, like that box plot setup, compared to, which in this case the data is the same, but if we were looking at like a small amount of data, I feel like getting the interquartile range would be pretty easy, especially if it's close data. But if it's something that's really serious where you need the mean absolute deviation, then it would make sense. I can see if you were like adjusting fuel tables or something, then you want it to be as precise as possible. You wouldn't want it to be scattered throughout the RPM range. You would want it to be correct, So I don't know. That's my thoughts on it. But anyways, what we're going to do is I told you that we were going to use a resource, and the resource that we're going to be using today is khanacademy.org. And so I'm going to put in our chat a website, and we're going to go to it. We'll work one together, and then you're going to be responsible for working the rest on your own. So I'm going to go to that now. And so this is a free website that's available to anyone. So if you're watching this online and you never used this, it's a very great resource to try. So looking at this, we have our mean absolute deviation that we've been studying. Now, this is something that most of us learned in the 6th grade. However, COVID struck last year and a lot of people did not get to this. So since they didn't, that's why we're covering it now. So looking at this, it says a family went out to eat. Below is the number of corn dogs that each of the 4 people ate. One of them ate 1.5, one ate 0, one was starving and ate 4, and the other person ate 2.5. 4 corn dogs. I'd be wanting to throw up. All right, so before we can find the mean absolute deviation of this data set, what do we have to find first?
The total number of corn dogs eaten.
Correct. And then we need to find the what? Starts with an M.
The minimum and the maximum.
Well, no, we don't have to do that. We can just get the mean. So we're going to add these together. So what's 2.5 plus 1.5?
4.
All right. What's 4 plus 4?
8.
Correct. And how many people ate corn dogs?
4.
So we need to do what divided by what to get our mean?
8 divided by 4.
Which is?
2.
So 2 is our mean. So what do I need to do to find my mean absolute deviation now? I got to do something with this 2.
You have to find how far away each
Correct.
number is from the mean.
Correct. So
And then
2.5
add it all.
minus 2 is?
2.5.
Good. So I'm going to just put 0.5 so that we can put it in the calculator. 4 minus 2 is?
2.
2 minus 0 is?
2.
2 minus 1.5 is?
1.5.
Yep. So we got a half plus a half is?
1 whole.
And 2 plus 2 is?
4.
What's 4 plus 1?
5.
All right. And how many people were there?
4. So 5 divided by 4.
Which is? Think about dollars. Think about quarters.
1.25.
There you go. So the MAD is 1.25. Perfect. We got it right, but now we got 3 more to do. Now these 3 are going to be on your own to do. So that's actually going to conclude my help for the day, and that will conclude our video for the day. So I will see you on the next block.